Okay, we're going to take a look at the last section of new material here in Unit 5, solving special systems. So to just recap, we're looking at a system of two equations. When you graph them, those equations are lines, and we're looking for the point of intersection. We can solve by actually graphing them and then hoping that our graph is accurate. We can solve it by an algebraic method called substitution, where we take the one equation, solve it, substitute it into the other equation. Or we can work with both equations together, add them together somehow to eliminate one of the variables. But up to this point, every single problem that you've been given, each of the examples that I've done for you, have been lines that intersect and have exactly one solution. Now's the time for you to understand that's not always going to be the case. So if I go here and choose some random numbers and create some systems of equations based on those random numbers, let's see what happens. So just pulling some of the numbers that were generated there at random, I'll get an equation 2x plus 4y equals 6, and then a second equation 10x plus 6y equals 10. If I put them into slope-intercept form by subtracting the x term from both sides first, I'll get y equals negative 1 half x, again reduce things, plus 3 halves for the first equation, and y is equal to negative 5/3 x plus 5/3 for the second equation. For the sake of speeding these things up, I'm going to use my graphing calculator. So here those two lines graphed, and clearly they intersect. And it's not always a pretty point, but clearly they do intersect. There's We've seen this over and over again. But the chart that's showing us here says there are two other possibilities. Let's take a look at a pair of another. Again, I'm going to take these and transform them into slope-intercept form. So the first equation becomes y is equal to negative 3 halves x plus 3. The second one becomes y is equal to negative 3 halves x plus 2. That's interesting equations there. What's the graph look like? When we take a look at a graph of both of these lines, oh, hold on, this is different. Here we had lines that intersect, and one of the first things that you have to notice here is with that first pair of examples, the slopes were different. Now, both of them were negative, so left to right, it looks like we're going downhill. But because the slopes are different, eventually they're going to cross somewhere. In this case, the slopes are both negative, but the slopes are the same. In this case, they're both negative 3 halves. Because this first one here has a y-intercept at 0, 3, and this second one has a y-intercept at 0, 2, these are parallel to one another. There is no point of intersection, so there's no solution. We get one solution if we have intersecting lines. We get no solution if we have parallel lines. We know we're going to get one solution if we can figure out the slopes of both of those lines and we find out that they're different. That's it. End of discussion. If the slopes are different, then they will intersect. There will be one solution. For parallel lines, the slopes are equal, but there's a second condition. What did we see here with that first example and with this random graph that I've drawn here? The y-intercepts are different, meaning that the lines are separated from one another by a certain distance. That makes them parallel. There's a third possibility here where we could get an infinite number of solutions. Let's look at this pair of equations, 2x plus 3y equals 9 and 4x plus 6y equals 6. Notice anything interesting about those numbers so far? If I put both of those into slope-intercept form, you'll notice again, we get the exact same slope, but we get different y-intercepts. Okay, so these lines turn out to be parallel to one another. What if I change just one of those original numbers? Suppose that second equation says 4x plus 6y equals 18. Now subtract 4x from both sides, divide by divide by 6. 18 divided by 6 isn't 1. 18 divided by 6 is 3. When I take those equations that looked, nothing really interesting at the start, when I put them in slope-intercept form and reduce the equations, I get the exact same thing. This time I typed in the equations without reducing. So for the first one there, yeah, it was negative 2 over 3 for the slope. For the second one, it's negative 4 over 6, and we saw that reduces down to 2 over 3. For the first one, 9 over 3, we should reduce that down to 3. And for the second one here, 18 over 6, that reduces down to 3. They both have the same y-intercept. You don't see two different lines here because in this case, the one line is exactly on top of the other line. We say that this is a simultaneous solution. Simultaneous, simultaneous. Whoops, simultaneous, sorry. simultaneous. How do we know that we get a simultaneous system here? The slopes are equal. And they have the same y-intercept. The graph looks like just one line because, again, the one is exactly on top of the other. Now, granted, you guys don't have graphing calculators. Shouldn't need them. I wanted to use the graphing calculator to show. I wanted you to get the visual. Here's how you're supposed to do this. The question is just going to ask, how many solutions does the system have? There's that pesky E word. Then If there is just one solution, find it. Okay, so for this first pair of equations, the first equation is given to us in standard form. The second one's already in slope-intercept. It's really hard to compare these and say, oh, these are parallel. No, they intersect. Unless we know the slope of both lines, that's not something I expect you to just look at it and be able to say. So let's transform this first equation into slope-intercept form. So again, from standard to slope-intercept, the first step is subtracting 3x from both sides. So we get 6y equals negative 3x minus 6. Oh, be so very careful with those signs. And again, I'm trying to get it to look like y equals mx plus b. So that's why I'm always going to put the x term in front of the constant. But I don't want to know what 6y is. I want to know what y is. So now divide by 6. Always simplify. Always reduce. So 6y divided by 6 gives me 1y. That's what I need for slope-intercept. Y equals mx plus b. Negative 3 over positive 6, that'll reduce down to 1/2 x. And negative 6 divided by 6 is negative 1. So we can say that for the first line, the slope is negative 1/2. For the second line, that was already in slope-intercept form. Don't have to do anything at all to that except for read m, the slope, is negative 5. Don't say negative 5x. M is the slope, x is the variable. The slope of the second line is negative 5. These two lines have slopes that are different. They have to intersect somewhere. Now again, the directions say if there's one solution, we're supposed to find it. Because the slopes are different, we know this should have one solution. Now again, if we've already taken the time and effort here to put the two equations in slope-intercept form, we could do the substitution method. If y is equal to negative 1/2 x minus 1 and y is equal to negative 5x minus 1 for our point of intersection, we set them equal to one another. I know, some of you won't like those fractions. That's not the only way that we've talked about this. If we want to use the elimination method, we're going to have to do something to that second equation in order to get things to line up properly. We could use substitution in a different way and take this and substitute it into that first equation and maybe avoid the fractions. So with the first equation said 3x plus 6y equals negative 6. If I take out the y and I substitute that entire expression, negative 5x minus 1, in place of the y, again, I get one new equation with only one variable. However, I need to do that by substitution the one way, substitution the other way, or the elimination method. That's got to be the goal of our very next step. Let's solve. First thing to do would be distribute the 6. Let's combine like terms. 3x minus 30x. Again, those are on the same side of the equal sign. Those just, 3 minus 30 is negative 27. Then I'd put the constants over on the right by adding 6 to both sides. Oh, wait a minute. That makes the next step of dividing really easy. because 0 divided by anything is still 0. If I have nothing, I can divide it into however many parts, I still have nothing. So again, that's one of the coordinates of this one point of intersection. Again, we said it had one solution. Now we're going to take that x and solve for y. Go back, maybe substitute it into this first one here, or maybe the second one, and say y is equal to negative 5 times 0 minus 1. Well, negative 5 times 0 is 0. Y equals negative 1. The point of intersection here appears to be at the point 0, negative 1. And again, you should come back and check it with this second equation. 3 times 0 is, well, 0. 6 times negative 1 is negative 6. So again, this first example here, we need to compare slopes. That's the first part of the process. Explain what we found because of the slopes. In this case, there was some extra work because there was one solution. They told us to find it. Let's take a look at the next one here. How many solutions does this system have? Well, again, in this case, we need to put both of them in slope-intercept form. So let's do that now. Use inverse operations to move the x to the other side. So for the first one, we'll add 6x. For the second one, we'll subtract 3x. Then divide by the y coefficient. So for the first equation, divide by 4. 6 over 4 reduces down to positive 3 over 2. And 10 over 4, well, we can reduce that down to 5 over 2. For the second equation, divide everything by negative 2. Negative 3 divided by negative 2 is, positive 3/2. Look at that. They have the same slope. But then finish it. Take negative 5 divided by negative 2. This is a system that has an infinite number of solutions. Those are simultaneous lines. Again, we can see here and here, slopes are equal. We can see here and here, they have the same y-intercept. So again, it's not enough to just look at the slopes because there are 3 different outcomes. If the slopes are different, we know they intersect. There should be one solution. We should be able to find it. We have 3 different ways of doing it. If the slopes are the same, then you need to take that next step and look at the y-intercept to see if they're the same. Let's see what happens in example 3. Again, the equations are in standard form. Let's put them in slope-intercept. For the first equation, we'll subtract 3x and then divide everything by negative 3. Well, negative 3 divided by negative 3, that turns that into just 1x. And again, we usually don't write the 1. But then negative 16 divided by 3, we can't reduce that. For the second equation, we'll add 6x to both sides and then divide everything by 6. Well, 6 divided by 6 is 1. So again, it's implied here. This has a slope of 1 and that has a slope of 1. These two have slopes that are equal. But then our value here for B is not the same. These lines are parallel. There is no solution because there is no point of intersection. So basically, we're putting together all of the skills that we've talked about, okay? Taking an equation and putting it in slope-intercept form so we can first of all compare their slopes. And if something interesting happens with the slopes so that they're equal, then we've got to take the next step and compare their y-intercepts. If they have different y-intercepts, there's no solution because the lines are parallel. If they have the same slope and the same y-intercept, this is a simultaneous system of equations. There's an infinite number of points of intersection. If the slopes are different from the start, that means they intersect and there's only one solution. All right, hopefully that all makes sense. I'll see you in class.